In organic chemistry, we're usually talking about synthesizing things, but sometimes we're talking about separating different molecules based on their physical properties. And that means that we have to understand intermolecular forces of different types of molecules because that is going to impact their physical properties such as boiling point, melting point, etc. Their solubility too, that's something that's going to be huge this chapter is solubility. So when we think about carboxylic acids, here are 4 different molecules. This one's a carboxylic acid. We have to say what kind of intermolecular forces are they going to have? This is a topic that we've done for a lot of different functional groups. And the 3 different types of intermolecular forces that a molecule could have are van der Waals forces, dipole-dipole forces, and hydrogen bonding. And what we're doing right now is on page 2, the note packet. So the question is, what intermolecular forces are carboxylic acids going to have? So pause it, and then check off the ones that it's going to have, and then unpause. Boop. All right. So carboxylic acids are going to have all of these types of forces: van der Waals, dipole-dipole, and H bonding. Dipole means the molecule has a dipole. So if we look at something like acetic acid, these are going to be polarized bonds, which are going to make this a polar molecule. All organic molecules have van der Waals forces. That's something we talked about a lot last semester. And what about H bonding? H bonding means that an atom has a highly polarized atom to hydrogen bond. This oxygen-hydrogen bond here can hydrogen bond. And it's talking about an intermolecular force. This is an OH covalent bond. If we have another molecule of acetic acid, that can H bond to this. So it's not a full bond, it's a partial bond. So these would be 2 molecules of acetic acid hydrogen bonding to each other. So these are H bonds here, H bonds. And it's the strongest type of intermolecular force, so it gives rise to strong intermolecular forces. So we have these 4 molecules over here. So the question with these is, which is going to have the highest boiling point? Which of these has the highest boiling point? And what we see in the note packet is that they all have roughly 58 to 60 grams per mole. That's their molecular weight. So compounds usually have more intermolecular forces the larger they are, but all of these 4 molecules are around the same size. So which of these would you expect to have the highest boiling point? And if you expect it to have the highest boiling point, that means that you also expect that it has the highest amount of intermolecular forces. So go ahead and pause again and select which would have the highest and lowest boiling point. Boop. Okay, great. So these 2 both have van der Waals, dipole-dipole, and H bonding. This one only has van der Waals. This one has van der Waals and dipole-dipole. So these 2 have the most types of intermolecular forces, so they should be the highest as far as boiling point. And it turns out that carboxylic acids have more intermolecular forces than alcohols. So we can see that in the boiling point. The boiling point of acetic acid is 118 degrees Celsius. This is propanol. The boiling point of propanol is 97 degrees Celsius. So relatively close between those 2, but you see that the carboxylic acid has a higher boiling point. What about, how does that compare to these 2? These 2 can hydrogen bond, these 2 cannot. I said hydrogen bonding is the most important intermolecular force. We get a very large difference between these and these. The aldehyde molecule has a boiling point of 48 degrees Celsius, so a lot lower than these. And butane boils at 0 degrees Celsius, so very, very low. So ultimately, those intermolecular forces give rise to higher boiling points, higher melting points. What about the carboxylic acid structure? So we have carboxylic acid here, and in the notes, we're asking what's the hybridization of that position right here. So go ahead and pause your video and add in what the hybridization is of that carbon atom. Unpaused, it is an sp2 carbon atom. It's a carbon that has three different groups, this oxygen, that carbon, so it needs three hybrid orbitals, so it's sp2 hybridized with three sp2 orbitals, one p orbital. What about this oxygen here? Go ahead and pause that again. The hybridization of that oxygen, because of conjugation, is going to be sp2. It's a hybridized. It's hybridized to have three groups because one of these lone pairs is in a p orbital. So we could say this lone pair in a p orbital. We know that one's in a p orbital because it's overlapping into that pi system, whereas this lone pair here is in an sp2 orbital. Okay, so that is the hybridization. Now, what I was asking you guys to do, we'll just get a whole new section of the board for this, is compare the bond length of this CO bond, so length, compare the length of that bond to the bond in ethanol. So this bond here is 143 picometers. So do we think that this bond is going to be longer or shorter than 143 picometers? Boop, pause, boop, unpause. It's going to be a shorter bond. It has, for one thing, this oxygen here is sp3 hybridized, so it's going to have longer bonds because of that. But we can also see that it has partial double bond character because of that resonance structure. So again, if we draw that resonance structure the whole way in, we see that there is double bond character here that would make it a shorter bond when compared to the other carbon-oxygen bond. So that kind of finishes out the physical properties of carboxylic acids on the top half of this page. But how do we synthesize carboxylic acids? Well, we've already learned various methods of doing that. The first set of conditions that we have here shows propanol going to propanoic acid. So what conditions did we learn to do this? This was that Jones oxidation. So Jones oxidation. This was a chapter 12 reaction that we learned. It's those chromium 6+ reagents. So the most common way that I wrote this was CrO3 with sulfuric acid. So if you don't remember this, and there's water around too, if you don't remember this reaction, if you go back to your notes from chapter 12, we walked through the whole mechanism of how an alcohol becomes a carboxylic acid in that chapter. So that is the best way to make carboxylic acids. The only other way that was in the same chapter was actually the oxidative cleavage of alkynes, and that was done with ozonolysis. I didn't pay a lot of attention to this reaction because, truthfully, it's not really used very much in the real world, so I kind of skipped over it, but it's in the notes, so I just want to make sure we get everything in there. But essentially, when we oxidize an alkyne with ozone, it forms, this half of the molecule forms a carboxylic acid, and this half does as well. So that one molecule goes to 2 molecules of propanoic acid. So those are the 2 ways that you guys have seen carboxylic acids formed this semester. So let me know if you have any questions about that stuff, and I will answer them if you do.